In this module, we'll be discussing mass balances. Mass balances have many applications in environmental systems. They're used to model the production and destruction of pollutants in the environment. They're used to predict the oxygen balance in streams and rivers, which is very important to measuring the water quality. We will apply mass balances in a lesson plan on dissolved oxygen sag in rivers this semester. They're also used to aid reactor design for water treatment, wastewater treatment, air pollution control, and solid waste management. Mass balances are an expression of the law of conservation of mass. Without nuclear reaction, matter can neither be created nor destroyed. This does not mean that the chemical structure and physical form of the matter does not change. For instance, in this class we will consider the reaction of carbon dioxide with water to form carbonic acid. The chemical reaction can be expressed as gaseous CO2 plus water forms carbonic acid, which is aqueous. Recall that any reaction rate has a rate constant, K, and so if this is a first-order reaction, we can express the rate of this reaction in terms of negative K concentration, where concentration being considered as that of CO2. Mass balances can be considered as an accounting exercise. When considering your bank account, the balance of money at any given time is equal to the deposits minus the withdrawals plus or minus any interest that has been accrued or taken. You can take the same approach to matter. When accounting for mass in environmental systems, reactions do not typically occur instantaneously, but they occur over time. So we typically express the accumulation of mass as a rate function. This can be written as d sub m dt, where m equals mass, is the change of mass in minus the change of mass out plus or minus any reaction rate that occurs. Now in engineered systems, we have a few easily measured quantities. The first of these is concentration C, which is equal to mass over volume. A typical measure of C is milligrams per liter. A second convenient measurement is flow rate, Q, which is equal to volume over time. A typical flow rate may be liters per day. When you multiply C times Q, you can see that the units cancel out such that you're left with mass per time. For reaction rates, the rate term is given units of concentration per time, or mass per volume time. When you multiply rate times volume, you'll see that the concentrations yield mass per time. So if we rewrite the expression for mass balance in these convenient terms, we'll see that the original expression, d sub m dt, can be rewritten as d cv dt is equal to the concentration coming in times the flow rate coming in minus the concentration going out times the flow rate going out plus or minus the reaction rate times the volume. And each of these have units of mass per time. I'd like to introduce the term hydraulic residence time now. Hydraulic residence time is given the symbol tau in some textbooks, or in your textbook, T of 0. In a completely mixed system, this term is equal to V over Q. The hydraulic residence time represents the average time a droplet of water remains in a system. The mass balance term can be rewritten to express hydraulic residence time. If you take this expression and you divide throughout by 1 over V, and you assume that the flow rate in equals the flow rate out such that those two terms are equal, you can write this in terms of tau. This term is equal to 1 over tau. This form of the mass balance is typical for a continuous flow system that is completely mixed. The mass balance can be rewritten in several forms depending on the situation. I'm going to take you through a few of these. When the pollutant is conservative, which means that the pollutant does not react, does not decompose, or does not form in the system, then the transformation term drops out from the mass balance. This term goes to 0, and the mass balance can be simplified as dCV dt equals concentration in, flow rate in, minus concentration out, flow rate out. We can also assume something called steady state. Steady state is defined when there is no accumulation of mass with time. That is the qualitative definition. This can be written quantitatively as dCV dt, or the rate of accumulation over time, equals 0. When steady state is assumed, the accumulation rate goes to 0, and the expression can be written as Cn Qn minus Cout Qout plus or minus the reaction rate times the volume. Steady state is a good assumption when you're designing a system that you hope has stable operation, or when you're looking at an environmental process that takes a long time to change, such as a lake or an ocean. Steady state is not defined as equilibrium. It is possible for a reaction, a chemical reaction, to not be at equilibrium, but for steady state to be reached. This would be true in a fast-moving system. In the next slide, I'd like to delve into this reaction term R. The reaction rate, which we've been defining as R, comes from the chemical reaction kinetics. From chemistry, you should recall that reactions can be zero order, first order, second order, etc. The reaction rate of a chemical reaction is defined as a function of the reaction constant K according to the reaction kinetics. In the examples below, I am going to remind you of zero order, first order, and second order reactions. What these graphs show are three different systems with the concentration plotted against time for a chemical reaction. For a zero order reaction, if we look at a decay rate, the rate of the reaction is independent of the concentration, and so the rate of the reaction, R, is equal to negative K. In a first order reaction, the decay of a substance is a function of the reaction constant times the concentration of the reactant at any given time. In a second order reaction, the reaction rate is equal to the reaction constant times the square of the concentration of the reactant at any given time. So if we go back to the expression of the mass balance, we can substitute the explicit rate term into the mathematical form. For a first order reaction at steady state, now you should note that once you solve a mass balance and all terms are defined, the mass balance should close, which means that the rate of the mass in minus the rate of the mass out plus or minus the transformation rate minus the accumulation rate should equal 0. This is useful when trying to define an environmental system where some of the inputs and outputs might be unknown, or where you may have to assume that some are negligible. If you make that assumption, you can always check your assumption by seeing if the mass balance closes. If it doesn't, your assumption is incorrect, and in the real world you would have to go define those inputs or outputs more carefully. This can also be useful in your homework to check that your solution is correct. We'll start by looking at a lake. In the next picture, I'm going to show you an environmental system that has several inputs and outputs to a lake. If we were approaching this lake system, the first step is to define the system boundaries. Since we're interested in what's happening in the lake, I'm going to draw the system boundary surrounding that. Using the system boundary, we'll be able to say what is coming into this lake and what's going out. So right away we see that there's a river going in, a river going out, a stream going out, groundwater interaction, and evaporation to the atmosphere. So we could draw this system in a simplified manner and place terms for each of the arrows. I'm going to say there's mass going in for the river, mass going in and out for groundwater, mass going out for a river 2, mass going out for a stream, and mass going out for evaporation. Now to simplify this, some of these inputs and outputs would be negligible for the mass entering in the river, which would dominate this system. To simplify mass balance, I would neglect evaporation perhaps, and neglect groundwater interaction. Okay, let's apply this for an example. In this example, a lake is receiving flow from a pristine stream, but an industrial polluter is dumping untreated sewage with a pollutant concentration of 180 milligrams per liter. The lake has a volume of 100,000 meters cubed, and the pollutant is decaying with first-order kinetics. The problem statement asks to find the steady state concentration of the pollutant in the lake. Okay, so I'm going to set this problem up the way I'm asking you to do in your homework. And it says that steady state can be assumed. Okay, in this problem we have a lake, we have a river entering the lake, and we have a polluter dumping into the lake. The problem statement said that the volume was equal to 100,000 meter cubed. I'm going to assume that that remains constant, and for that to remain constant there has to be a flow rate leaving the lake that is equal to the two inputs. So QR plus QP. It's always good to list your assumptions. And I'm going to assume that when the problem statement said that the river was pristine, that meant that the concentration of the river of the pollutant was near zero. Alright, so I'm going to set up my mass balance with those things in mind, and I'm going to say steady state dCV dt equals 0. And so what's coming in, CR QR plus CP QP minus the concentration going out times the flow rate going out minus the decay rate times the volume. We assumed that the concentration of the river, since it's pristine, is negligible. And we also assumed a completely mixed system. So in a completely mixed system, the concentration going out would equal the concentration in the river. And I'm going to take this to that side of the equation, and now I will solve for C out. Okay, I'm going to start putting in the actual numbers to... Okay, so the concentration of the pollutant was 180 milligrams per liter, and the flow rate of the pollutant was 430 meter cubed per day. We need to get our volumes to cancel out, and there are 1,000 liters per meter cubed. The flow rate of the river was 4,000 meter cubed per day, plus 430 meter cubed per day for the flow rate of the pollution, plus 0.70 inverse days for the decay constant, times the volume, which was 100,000 meter cubed. And I'm going to convert meter cubed to liter, and this gives us 1.04 milligram per liter.